Hey everyone, this video is going to give you an introduction to CFA. So the easiest way to explain CFA is to compare it to EFA. So if we have 6 items that says, in the last 2 weeks I have felt, and they rate agree to disagree on these items, we can see that it's likely to group into 2 different ideas. We've got people who are a little bit more of a positive affect and some people who are a little bit more of a negative affect. And that's exactly what we see with the Pearson correlation in EFA. We run correlations between all the items, and we're seeing that the positive ones are grouping together and the negative ones are grouping together. We can see the same thing in our factor loadings. So we run EFA, we get our factor loadings, and we see that these items are loading on the first factor, these items are loading on the second factor, no cross-loading, these are all quite low. We have a really nice 2-factor structure based on EFA. Well, what EFA is doing, if we think about it in SEM notation, is we have all of these items and we are allowing them to load on 2 different ideas, 2 different factors. And we can see that these load heavily on positive and these don't. And these load heavily on the negative, and these don't. But they are still getting the option to load on these. What confirmatory factor analysis does is it says, we're not even going to bother loading on the other factors when these 3 should conceptually load on positive, these 3 should conceptually load on negative, and that's all we're going to do it. We're going to basically force them to load here and see what happens. I have shown you a little hint at some of the simultaneous equations for path analysis. When it comes to EFA and CFA, it's all based on matrix algebra. So we have all of this and how they relate to each other, and we get more complicated and more complicated and more complicated, and I need you to know that it's based on matrix algebra. You're welcome. So with CFA, we're really trying to find an optimal model. And we're probably going to be generating multiple plausible models. There is rarely an occasion where we're just looking at one because we need to compare different model options. So in the example I just gave you, we could load all of the items onto one factor. It is possible that there's not a positive and a negative. It's possible that there is one overarching factor and we load everything and see what happens. The second model in this example would definitely be the 2-factor. So having the positive items load on the positive and the negative items load towards the negative. It's very logically sound and we should try it. There are other times where you could have a confusing item or a concerning item, or an item that in other EFAs have shown to cross-load. We could actually cross-load one item on 2 factors, run the whole model, and see what happens. There is a final thing that might happen, which is very strange, but it could be that AMOS will provide suggestions for model improvement. One of the ways it does this is correlating error terms. I'll show you what that looks like. So what we do is we're going to run the models and then we'll compare all the fit indices. When we compare everything and you see all these fit indices side by side, then you choose the best fitting model and preferably the one that is the most theoretically sound. So you could have a really good fitting model that doesn't really match the theory that you started with, and that's not the most best fitting model. So here's how you would actually consider a cross-loading item. So SAD would have to have some other literature, some background that has shown me that it has potential to load on both. And I could test it. I would run with it loading on one, loading on the other, loading together, see what happens. In this case, we can see that these did change. So it actually affected more in the model than just it. And it's still loading really heavily on negative, not really loading very much on positive, and overall it's not adding much to the variance explained. The model fits also, in this case, didn't really change that much. So in general, not really worth it. I mentioned the idea of a correlated residual. You can think of this as conceptually it is making the model more stable, that it is just making it work better. And a lot of times this would be a suggestion that Amos gives you to improve your model fit. So in this case, we're actually correlating the error terms on down and unhappy right here. We can correlate terms across items too. And in this case, it actually improved the model fit pretty considerably. So this one would be an admissible solution. So we get better estimates across multiple places just because we correlated these two error terms. And all of a sudden we have really good fit across all of our things. But is that theoretically sound? Does it make sense for great and for sad to vary, their errors to vary together? Maybe, maybe not. But you're going to have to make that argument if you choose to correlate errors. So again, the whole idea is to compare models. So we're going to choose fit statistics that we want to compare. There's a whole list of fit statistics. You get to choose which ones you're going to use. And I highly recommend creating a list or a table even to easily compare across all models. This table is really nice to put into articles or presentations. It is also very likely that Model 1 will look good on CFI, but Model 2 will look good on RMSEA, and Model 3 sucks on all of them. Who knows? But it's not usually as obvious as you would like it to be, most unfortunately. And it comes down to you get to choose, but you need to make sure that the theory matches, especially if you're capitalizing on the model improvement recommendations that could be based on chance. But you need to be able to defend your decisions. So here's an example. I was just recently working on a psychology measure that's super well known in the field. It's used all the time, but it hasn't been examined very often. Well, it's been examined heavily with EFA, but not with CFA. So we ran 4 different models. I started off running all of the items on one factor. I did this because I wanted it to give us a baseline and to show that that is not a good fit. There are a lot of researchers who use a measure and they will just add up or average all of these items together into one score that is not logically sound, but they will use it in practice. There is also very considerable debate in the literature on if it is a 5-factor structure or if there is a 4-factor structure. And the major difference between the 4 and the 5 is we dropped this guy right here. That he didn't really fit, the items were very sketchy, loading on this guy and then compared to everything else. And so we wanted to try it with 5 and dropping this guy with 4. The 2-factor structure actually groups these two together and these two together. And what we found is it was very confusing. So all of the chi-squares were significant and looked great. So overall model fit, fantastic. CFI, if you remember, should be above a 0.9. So none of these are good. RMSEA should be below a 0.1. So none of these are really that great. That one's okay. But the CFI is better with the 4-factor, but the RMSEA is better with the 5-factor. The 2-factor we can just cross off, and the 1-factor is a huge mess and definitely not the way to go. So which one do we choose? The 4-factor or the 5-factor? Well, we got to go back to theory, and it really comes down to how important is this guy? Do we need this factor in there for the theoretical reasoning, for a practitioner reasoning? What is it? Or can we drop this and say the 5, we really support the 4-factor structure? Again, completely depends on you.